Benedikt, and he's going to, from Graz University of Technology. He's going to present parameterized infinite state reactive synthesis.
Yeah, thanks for the introduction. So let me first talk a little bit about what this title actually means. So I guess most of you are more interested in like sequential programs or functional programs where you take inputs once and then do some complicated computation, and they're interested in one output afterwards. Oh, sorry, let me double check. It was working before, sorry for that. Okay, sorry for that. Let me start again. So we're interested in reactive systems. So what do I mean by reactive system? So as I said before, we're not interested in a single function that takes inputs at the beginning and computes some result in the end, but instead we're interested in a system, like you see here, that is interacting with some environment. So in every time step, it receives some information, some inputs from an environment, does some computation, can update some of its internal state, and then it sends back some result of this computation to the environment. And these two parts, or sometimes also referred to as players, are interacting continuously with each other. And this gives us some infinite trace, so if you don't stop it, then it just keeps running forever. And you're interested in specifying the behavior of this system over these infinite traces. And then we want to synthesize some system or some program that satisfies some specification over this computation trace. And we will use something called temporal logic, or a form of temporal logic, to specify these expected behaviors. And then we want to find one program that actually satisfies this for all possible environments we could use. So let me show you a small example. So we have this cute robot here that is standing on some track. So let's start by modeling this in form of temporal logic, or in the infinite state temporal logic. So let's first introduce a state variable, let's call x, which is a real valued variable, and it defines the position of the robot on the track. And then the robot should also be able to do something. Just standing there is boring. So it can move to the left or to the right, or it can just not move. So this gives us three possible actions that the robot can choose from. And now I also said there is some interaction with an environment. So let's add some adversarial environment to that. So we have this little daemon here that is trying to push the robot around. So it can also push it either in one direction or in the other direction, and it can choose any value between -1 and +1 for pushing it. So this might also be some fractional value or something, which results then in an infinite state system. So now we have the options for how the system can behave and how the environment can behave. So now we also want to, as I said, specify what is a good behavior of this system. So the first one is we don't want our robot to fall off the track. So the daemon should not be able to push it off the track. So let's add an invariant that in every time step we have to be on the track. But just staying there is not very productive. So we want our robot to also do some work. And for that, or in this example, it should move boxes from some pickup area and load them onto a ship. And in an abstract sense, we'll model this by just being in the area where the boxes are and being in the area where the ship is, both infinitely often. And this infinitely often in linear temporal logic, which we're using here, is notated by this square and diamond operators. So here it says be in both regions infinitely often. And if you look carefully and think through this example, you might notice that this isn't really implementable as it's shown here. Because what if the robot is just constantly pushing with maximum force in one direction? Then we cannot move and get anywhere closer to the target. So we'll also extend our temporal logic specification by adding some assumptions on how the environment should behave. In this case, it is we expect the environment to both push in the left direction and in the right direction, again, infinitely often. And this specification that results there falls then into a fragment that is called GR1, which has these some things happen infinitely often as assumptions and also on the guarantee side. We'll need a bit of this structure, but the exact details aren't super important for this talk. So one thing that this GR1 structure gives us is we can take this formula that we had before for the temporal logic formula and get some first sketch for how an implementation should look like. And first thing is we introduce a new variable. Here it's called C that keeps track of if we are trying to pick up a box or if we are trying to load the box onto the ship. And then we get two strategies, one for go into the area of the box, and the second one for go into the area of the ship. And also we have a third component, which is shown at the top, which checks if have we currently satisfied one of our guarantees, then we should change our strategy and work towards the next goal or the next strategy. And in this case, these just alternate, and if both of them reach their goal whenever it's their turn, and they change between each other, then we would have a strategy that infinitely often reaches both of these targets. So now let's try to fill in these if conditions, and just if you do it manually, we could, for example, plug in this. If you just focus on the highlighted area, then we would have for reaching the boxes, we should go to the left as long as this would not lead us to falling off the track. In that case, we just stop, and if you want to go left, then there is never a reason to go right. And the other strategy for getting to the ship works, works the same. You can also remove the false branches, and I'm using this program from now on. So the other part of the title was parameterized. So what do I mean by that, and why do we need that? So previously we had this example, which was with between at 1 is one area, at 9 is the other area. But what if I change this? What if my pickup area got moved to the location -2, and the boat got moved to the position 6? Or what if the ship or the boat is now 1,000 units away? I don't really want to rerun my synthesis tool with these new parameters, or whenever I have a new environment, rerun the synthesis tool. So what I want to have instead is one parameterized program for this one parameterized specification. So here I can now say I have parameters like min and max that define some properties of my environment or of the problem in general, like the position of the boxes or the position of the ship. And then I want to have a single program that might use min and max and that works for all of these possible values I can plug in for min and max. So how do we tackle this problem? And for that we have two key observations. The first one is that if you use a tiny state space for this problem, then it's not too hard to synthesize this. So high complexity, but the small state space means it's still tractable. And the other observation is that the programs aren't that different. Just because I change a few numbers in my specification, I expect very similar output programs. So we want to exploit these two ideas in our algorithm. So our algorithm starts by plugging in some concrete numbers into this parameterized specification. And then we can run this through an existing synthesis tool, like a Tier 1 synthesis tool that works on these infinite state systems. And this gives us one concrete program, and it also gives us a certificate or an invariant that certifies that this is a correct program for these concrete values. Like, for example, using 0 and 2 gives me this program. So I have now, for the left program, the condition x plus d should be greater or equal to 1. Then I should go left. But now I need a second program, because just from this one program, it's a bit difficult to do anything. So let's repeat the same process, plug in some different numbers, and again, we get a concrete program and invariant or a certificate why this is a correct program. So now I change the numbers, and the program is almost the same, but there is some slight differences in there. So now that we have at least two programs and two certificates, we can try to generalize them. So from these example programs for concrete states, we want to infer one parameterized program that should work for all possible parameters. And also a certificate that is trying to certify that this program is actually correct. So let's first look at how we generalize these strategies. So how do we get from multiple concrete strategies into one candidate for a parameterized strategy? So we saw that these templates or this sketch we had for the program had like if conditions, and otherwise it was choosing between the actions. So we can now start by generalizing each one of these conditions or guards individually. So let's look at the two examples that we had before. So for 0 and 2, we had the condition x plus t should be greater or equal to 1. And for 1 and 3, we had x plus t is greater or equal to 2. So the first step in this generalization algorithm is to apply anti-unification to figure out where these guard conditions are the same and in which parts of the guard conditions they are different. So this would give us a new expression as shown below that says x plus t greater or equal. This is this shared between all the guards that we have seen. And then there is a whole that sometimes is 1 and sometimes is 2. So now we did a second part of our generalization approach that figures out what should we put into this hole. For this, we rely on syntax-guided synthesis, and we ask it just to, given that we know the values for our parameters and the values for this hole, can you come up with an expression that neatly expresses this difference? So here it might come up with maximum -1. It's a small, nice-looking expression that satisfies all the criteria that we have here. So to summarize this generalization part, we first have an anti-unification preprocessing step that figures out which parts of an expression are already the same. Then, using syntax-guided synthesis, we synthesize new expressions to fill the holes left over by the anti-unification part. And we also have a fallback method if we figure out that something is too different to work with this approach, then we more or less generate a decision tree, which I did not show in detail here. So using this method, we can apply it to the whole program, and we get this first candidate for the strategy. So here we have both programs more or less use the same condition. So both say x plus d, or like the inverted, but both use max -1. This kind of looks a bit weird, right? So if we want to go towards the boxes, our program just depends on how far away we are from the boat. And if you are close to the boat, that's not quite what we want. And that's where the last part of the algorithm comes in. We need to take the program and the certificate and cross-check those and see if we are actually found a program that generalizes to all situations that we might encounter, like to all parameter values. And doing so, we would figure out, no, that doesn't quite work. I'll go into a bit more details on how these certificates look and how we find these counterexamples in a moment. But for now, just accept that, no, this is not, this left sub-strategy doesn't really work. And we get new parameters like -4 and 0 for which it does not work. And now we can go back to the reactive synthesis module, the tier 1 synthesis module, and ask for a new program for these parameters. So we now get a third program. And we can now also include this in our generalization approach and infer this program that now fixed also the left sub-strategy and uses a more appropriate condition there. So as promised, how do these certificates and this cross-checking work exactly? So the first part is we have invariants. These we get automatically from the tier 1 solver. So we can just take these invariant expressions and also apply the same generalization as for the conditionals in the program and try to infer a new invariant that works for all the parameters we have already seen. And then we also need to somehow certify or check that we are actually reaching the guarantees. And this we do with a ranking argument for each one of these sub-strategies. So each of these sub-strategies should make progress towards the goal it is supposed to reach. And then after we have the ranking function and the invariance, we can ask an SMT solver, does this actually work for all possible parameters? So for these ranking functions or termination, we have like this loop. So run this sub-strategy until you reach the goal it's supposed to reach. And these ranking functions are like mostly standard ranking functions, so they should decrease in every step. But because we also have this tier 1 part with the assumptions, we need to like add a bit of plumbing to our ranking function that says for at least one of these assumptions we have on the environment, we should make progress. And otherwise, if none of the assumptions are true, we can also just stall. So based on the first program, we could get this ranking function candidate, where our ranking argument would just be x. We are always making progress by decreasing x. But that's not quite right, because as we would expect the ranking function should be positive, or like greater or equal to 0 or something. And x could be negative, like if we have -4 to 0 as our range for the problem. So we would get, when cross-checking, we would get these counterexamples. And then after we integrate this counterexample in our generalization approach, our ranking function synthesis should also come up with a better ranking function. And these, like this x minus min, would then also be a ranking function that correctly certifies this sub-strategy. So to summarize the procedure quickly, we start with the parameterized specification. We generate multiple concrete instantiations of it, and then run them through an existing synthesis tool, and then try to generalize both the programs and the proofs, and then cross-check them if we have found the correct program and proof pair. And if not, then we get some new counterexamples. Unfortunately, this whole process is also undecidable, so it might happen that we just run through this loop forever and just generate an infinite amount of new examples. We also implemented this in a prototype tool, and so it uses CVC5 for the Cygos part and C3 for the other game solving. And we have made also a different variant that skips this anti-unification part and just tries to do the whole generalization only with Zygus. And we also compare it to existing tools that don't support like this parameterized framework, but where we try to encode this with existing elements. And we have a small set of somewhat existing benchmarks that we added, where we added some parameters into it, some new ones that we created for this paper. And like the overall observation is that existing tools that don't natively support these parameterized specifications, they almost fail completely. So like one solved one benchmark, the other solved two benchmarks. And our tool solves most of these benchmarks in the configuration where it uses anti-unification preprocessing. If we turn this feature off, so just rely on Zygus, then about half of the benchmarks fail. Like all of them, the benchmarks that have a bit larger expressions, just using Zygus alone is not sufficient to find a good generalization. Okay, so thanks for your attention, and I'm happy to take any questions.
We have time for a couple of questions, please.
Hi, great talk. I'm curious, so anti-unification relies on like all of the program structure matching other than that parameter that you're anti-unifying.
Yes.
Right? And so, but the synthesizer can kind of spit out programs with all kinds of different structures. So I'm curious if you run into that issue a lot, if you have to do things either modifying the synthesizer to handle that better, or like canonicalizing, or yeah.
Yes, so there is quite a bit of normalization in there that I skipped over here. So one advantage of this, like just restricting ourselves to the tier 1 synthesis part, is that we can really use this this template here. Where is it? Like this one. So we already know that like we have one condition for each action and each sub-strategy. So this reduces the variability of the synthesis output already quite a bit. And then we also do some redundancy elimination on the SMD formulas that we get, so removing all kind of propositions that are not necessary, and they still preserve equality. And then we are also like sorting all commutative operators like alphabetically, so all the same variables should end up in the same position of the formula. But this is a bit of a heuristic, yes.
Thank you for nice speech. And in my understanding, there's a two-part generalization and verification. Yeah, and I found out that you synthesize a ranking function in the verification process, and I wonder why it is separated. I mean, those ranking functions cannot guide the generalization process?
Yeah, so why do we have to like synthesize why do we have to find these ranking functions in this verification part? Why are we just taking them from the synthesis result? We first tried just taking like the iterates from the like fixed point computation, but it turns out that those have like too much strange behavior in there, in that they are not just specifying a single program, but like all multiple possible implementations that would still be compatible with the results of the fixed point computation. And these kind of turn out to be too complicated for good ranking functions. And we want something that doesn't rely on how many iterations we did in our first synthesis. So like the synthesis approach tells us, okay, this is the set of ranking functions for rank 0, these are for rank 1, and these are for rank 2. But just having those 3 sets doesn't generalize on its own. So you need something that from knowing the first 3 sets of the ranking argument, figure out what is the 4th and 5th and 100th one. And for that, we're currently relying on again, on Cygers to figure out some ranking argument.
You probably mentioned this, but I just didn't catch it. What is the specific structure in this like reactive type of program that you're using? Because the big synthesis loop that you're showing, I can imagine, could be applied to any sort of parameterized program that is just like mapping some inputs to outputs.
Yes, you like. Where's my full overview slide? So this whole procedure with having a parameterized program and then just plug in some different synthesizer here. I think, yes, this would work in principle. It's mostly that we started from this reactive synthesis perspective. So we also spent some prior work on developing this first synthesis tool. And I think you could try doing this with other tools. So if you want to talk about that, I'm happy to do this afterwards.
Okay, we are running out of time. If you can speak later, maybe. Okay, sorry. Let's thank the speaker again.